If you're watching the recording of this session on YouTube, I invite you to join me next time live. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial on quantreasoning.com. So I'll stop you here. And let's just focus on the question itself. Ignore the statements for now. Can any of you try to rephrase what this question is really asking for? I mean, focus on just this part, from here to the end. Is the prime box of M a subset of the prime box of N? Am I understanding you correctly?
Yeah.
You're exactly right, JD, but what's a much simpler way to ask that? How would you explain this to your grandma? Exactly. Very good, Emmanuel. The number of students would be divisible by the number of classrooms evenly, meaning an equal number of students in each classroom if n is divisible by m. So that's what this question is asking. Is n divisible by m? And I think that's half the battle here, just figuring out what it is that the GMAT is trying to ask here. Is some number n divisible by some number m? Now they do tell us a little bit about the values of n and m. We know that they're positive integers. We know that n is at least 14, but there's no upper limit for n. So anywhere from 14 all the way up to infinity. For m, though, we have a much smaller set of possibilities, right? We know that m is definitely either 4, 5, 6, 7, 8, 9, 10, 11, or 12. Those are all the options for m. And I think it's a good idea, before we even go to the statements, to wonder, is it possible that n would be divisible by m? Like, are there numbers from 14 upwards that are divisible by some of the possibilities for m? For example, if m is 5, can you think of a value of n that's divisible by 5? Yeah, 15, 20, 25, really any multiple of 5 above 13 would work. What about the other way around? Can you think of a situation where n is not divisible by m? Yeah, any prime number above 13, because we know that n is above 13, but any prime above that, so 17, 19, 23, etc., by definition will not be divisible by m. Because the one thing we know about prime numbers is they're not divisible by anything other than 1 in themselves. So that's a very easy way to get a no. To get a no, that n is not divisible by m. If n is any prime number over 13, then the answer would be no. I think it's useful to take a few seconds to just go through all of that reasoning before we dive into the statements. So that's kind of a general piece of advice beyond this particular question. Just in general, for data sufficiency, it's good to take a few seconds and think about how we could get different answers before we start using the statements. Before we start evaluating the statements, I think it'll be a good idea for us to explore the concept of divisibility a little bit further, because this is a very hard question. Is 30,000 divisible by 48? Now, the long way to answer that is to try to divide 30,000 by 48. But we don't want to do that. And I'm going to propose that the better way to check divisibility is to look at the prime boxes. It goes back to what JD was saying earlier. Look at the prime box of 30,000 and look at the prime box of 48. And for those of you watching the recording on YouTube, I'll link a video that I did about prime boxing in the description below and also above me. The most efficient way to get the prime box of 30,000 is to split away the power of 10 like that, right? Because isn't it true that 30,000 is 3 times 10,000? And the reason this is very effective is because we know that tens are built of pairs of 2 and 5. Right? The prime numbers of 10 are 2 times 5. So in this case, we have 4 of them. So that means we're going to have 4 of these and 4 of these. And don't forget, we also have that 3 on the side. So the prime box of 30,000 looks like this. That's the prime box of 30,000. The prime box of 48, we've got 4 of these and 1 of these. Just taking that from there. So that's the prime box of 48. And now you can tell if you were to divide the top number by the bottom number, I mean, look what happens there. That gets reduced. That gets reduced. And the denominator is now gone. The denominator divides the numerator evenly. In fact, if we wanted to say what the answer is, we could just say the answer is 5 to the power of 4, right? 30,000 divided by 48 is 5 to the power of 4, which you might have even memorized as 625. My hope is that by doing this little exercise on the side here with 30,048, we're starting to gain a better understanding of what it means to be divisible. When you look at the prime boxes, you kind of see that as long as the contents of the prime box of the denominator are a subset of the contents of the numerator, then all of those factors from the denominator will cancel out, with matching factors on top, leading us to an integer. The division results in an integer, which means that the numerator is divisible by the denominator. So that's the big takeaway there. And I also want to point out that having the extra 5s, look at that, we have an extra 4 of them. And we've got 5 times 5 times 5 times 5 left over in the numerator. That's not a problem. Having leftover stuff in the numerator does not interfere with the divisibility. Think about that for a moment. Leftover stuff in the numerator does not prevent you from being divisible by something. Leftover stuff in the denominator, that's an issue, right? If you've reduced everything that you were able to reduce in the top and the bottom, and you still have leftover stuff in the denominator, well, guess what? It's not divisible. So that's a real problem if you have leftover stuff in the bottom. Leftover stuff in the top, hey, the more the merrier. Let me put that another way. If I'm some number, and you offer me a factor of 7, let's say, you're like, hey, Avi, whatever number you are, we're willing to give you a factor of 7 so that you'll be 7 times bigger than you were before. Can you imagine me saying, oh, you know what, guys, no thanks. I don't want that extra factor of 7 because I'm worried that it will mess up my divisibility. I'm worried that I will no longer be divisible by the stuff that I am currently divisible by. That would be nonsense. That's nonsensical. Having an extra factor of 7 won't eliminate any of my divisibility. It will just open up more divisibility. That's why I say the more the merrier. That's a very common mistake that people make on the GMAT is they think, oh, this number isn't divisible because it has too many of something. So all we need for divisibility is that everything in the bottom prime box is a subset. It fits into everything in the top prime box. Let's take another look now at the question itself, the original question. And perhaps we can start evaluating statement 1. So what is statement 1 saying exactly? That's right, 3n is divisible by m. Now we wanted to know, is n divisible by m? So I'm thinking about a way to visualize what they told us versus what we wanted to know. And I'm thinking, well, we could maybe say something like, the prime box of m is a subset of the prime box of 3n. So we're looking at prime boxes here. And this statement is telling us that the entire contents of the prime box of M are embedded within 3n. You could put maybe a ... there to illustrate that there may be extras, right? There could be more stuff than we needed in 3n, but in the very least, we know that 3n contains the prime box of M. And what we wanted to know is about n on its own, without that extra factor of 3. Right? This is the question. Can M fit fully within n without that extra 3? I mean, we're dividing by 3 as we go from left to right. We're losing a factor of 3. Does the loss of this factor of 3 mess up the divisibility? Could it mess up the divisibility? I think is a better question. What do you guys think? Is there a risk in losing that factor of 3? Is it possible that the divisibility worked for 3n only thanks to that 3, and without that 3, it would no longer be divisible by m? What do you think? Is that a risk? So what I hear you saying is you're concerned that maybe the only reason 3n is divisible by m is thanks to that 3 in 3n, and without it, it wouldn't be divisible by m. Yeah. And I think you're right. I think that would happen under what circumstances? If m has a 3 and n doesn't, and then 3n has that 3 that was required, but then when you go back to n on its own, you lose that 3. So I guess what I'm saying is if m doesn't have a 3 in its prime box, then we're fine. Right? If we knew that there were no 3s in the prime box of m, and we knew that 3n is divisible by m, then we would feel confident to say that losing that 3 is no big deal because m doesn't have any 3s, so we would be able to say that the 3 was unnecessary. It was just an extra. And losing the 3 when you go from 3n to n, that's fine because we didn't need that 3 in the first place. How do I know we didn't need it? Because we knew that m doesn't have any 3s in it. But as long as m could have a 3 in the prime box, then losing the 3 from 3n as we go to n could be a game changer. It could be a really big deal. That's interesting. And I think there's an important takeaway here, which I should make explicit. In the thinking that we did here, and in the diagram that I drew, I was very careful to go from what we know to what we want to know. We know something about 3n, we want to know something about n. And that direction of thinking is really important, and it's something that people mess up a lot. A lot of times people go in the opposite direction. They go, well, I want to know about n, and I know about 3n, and so they're going from n to 3n, and they're saying, well, I would multiply by 3 to get 3n. But that's the wrong way to think about it, because we don't know anything about n. We know about 3n. We know about the divisibility of 3n. We want to know about the divisibility of n, so it's important to go in that direction. And that's why I have this divided by 3 symbol to illustrate how we go from what we know to what we want to know. And then you can ask yourself, does losing that factor of 3 make a difference in terms of the divisibility? And the answer is it might, because if m has a 3 in it, then this extra 3, losing that extra 3 from 3n to n, could be a big deal. It could destroy, it could ruin our divisibility. Exactly, because I don't know if the 3 that I'm talking about is this 3, right, that extra 3. If that extra 3 was necessary for the divisibility, then losing it will destroy it. And if it wasn't necessary, then losing it is no big deal. So I can't actually answer the question here because I don't know whether or not that 3 was necessary for the divisibility described in statement 1. It might have been necessary because look back to what we know about M. Is it possible that M has a 3 in its prime box? Yeah, it could even have 2 of them. M could have 2 3s in its prime box. You know, guys, just for the exercise, let's write down all of the possible prime boxes for M. So we would start at 2 squared, because the smallest possible value for M is 4. And what will we have next? 5 to the 1. Then we have 2 to the 1, 3 to the 1, 7 to the 1, 2 cubed, 3 squared, 2 to the 1, 5 to the 1, 11 to the 1, 2 squared, 3 to the 1, and that's it. Those are all the possible prime boxes for M. Some of them have a 3, one of them has 2 3s. Some of them don't have 3s. So when I look at statement 1 and I ask myself, is that extra 3 necessary? The answer is maybe. I don't know. So given the information from statement 1, am I able to answer the question definitively? Can I say with any kind of certainty whether n on its own would be divisible by m without that extra 3? I don't know. So we would eliminate AD and we're left with BCE. Now that we've evaluated statement 1, what do you think about statement 2 on its own? Can you explain, Emmanuel? Why is it that statement 2 is sufficient even though statement 1, which seems very similar to statement 2, is not sufficient? Emmanuel is saying, look, we looked at all the possible prime boxes of M. None of them had a 13 in it. Of course, because 13 is a prime number and we were told M is less than 13. So 13 wouldn't appear in any of the possible prime boxes for M. Which means that if you're telling me that 13n is divisible by m, and we know that m doesn't have a 13 in it, therefore we can infer that this extra factor of 13 was unnecessary. You said that really well, Emmanuel. It's unnecessary. We don't need that extra factor of 13 to enable the divisibility that's described here in statement 2. Meaning, even without it, even if we divide that by 13 and go back to n, which is what the question is asking about, it's still going to be divisible by m because we didn't need that factor of 13 in the first place. And how do we know that? Because we know that m doesn't have a 13 in its prime box. The 13 was an unnecessary extra factor, so removing it won't mess up our divisibility by m. And we know that it was an unnecessary extra factor because we know that m doesn't have a 13 in its prime box. And that was given to us, or implied, I should say, here in the free info. But, the beauty of understanding divisibility at this level is you don't need to test cases. Typically, how people solve this question is they test a bunch of cases and maybe they get lucky or maybe they get unlucky. But we don't even need to go there if we really understand divisibility at that level of prime boxes. Yeah, no, I'm really not a fan of testing cases because it's really bad when you do it at home because then you didn't learn anything from the question. And if you're not learning anything, then why would your GMAT score improve? And when doing it at the test center, it's not as bad because, it's better than nothing, right? But it often causes people to run out of time. And then it's not better than nothing. Then it's actually worse than nothing. I'd rather just throw away that question than spend 5 minutes testing cases on it. Yeah, so what we are doing here with quantreasoning.com is in big part making it unnecessary to test cases. Go beyond testing cases. Because you shouldn't need to test cases if you really understand the concept that they're testing, as we saw here in this question. It's a great question, Emmanuel. I think of it a lot like bodybuilding, right? How do bodybuilders develop big muscles and the ability to lift heavy weights? It takes the right kind of effort, because the wrong kind of effort at the gym, you'll just get injured. So it takes the right kind of effort over time. It's not something that you want to work on more than, say, an hour or two on a given day. So that's just kind of high-level advice. But to be more specific, be curious, asking what if. What if this didn't say less than 13? What if it said less than or equal to 13? That's a really good habit, to just be curious about how things would change if you make a certain change in the question. I think the other important piece of advice is to never focus on picking the right answer, because it's really not interesting to pick the right answer when you're at home. You don't get anything out of picking the right answer. So I'm never really that curious to know, did I pick the right answer or not? Much more curious to know, what are they really testing here? How could they increase the difficulty level of this question? How could they build the same kind of question but on a different subject matter? Right? This question is asking about the area of a rectangle. How could they ask it instead about the product of unemployment rate and number of employable people? Because you could build the exact same question on those two different subject matters. I talk a bit about that in the preface to my book. So it really comes down to curiosity and unwillingness to be satisfied with just picking the right answer. Because if I was satisfied with just picking the right answer, I would test cases on the question that we just did. And it might take me 3, 4, 5, 6 minutes, but I'll pick the right answer and I'll say, oh, wow, that took a bit too long. Maybe if I just practice more questions, and that's where people go on Google and they find all these third-party questions from different test prep companies that are just not at all representative of what the GMAT is really testing. But they feel like, oh, I solved it by testing cases and it took 5 minutes. That means I need to do more questions. But they're wrong. It doesn't mean they need to do more questions. It means they didn't do it right. They shouldn't have been testing cases in the first place. They should have been developing their reasoning. That's the more specific advice that I would give, is never be satisfied with testing cases. Never be satisfied with tips or tricks on how to kind of get lucky with picking the right answer, because you don't get anything out of that. It's kind of funny that people really care about getting the right answer when they're at home. It's different at the test center. At the test center, the only thing that matters is get the right answer. But at home, who cares if you get the right answer? I actually prefer to get the wrong answer, because that means I actually can learn something from that question. I'm always a little bit disappointed when I pick the right answer. Like, oh, that was a waste of a question. I didn't learn anything from it. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.